Hello everyone. Welcome to this lecture based on chapter 3 of Domidenko's book. We have already discussed several topics, uh, including joint and marginal CDF, PDF, and PMF, expected value, independence, and conditional distribution. We have already finished those parts. In this lecture, we will be discussing about mixture distribution and Bayesian statistics. Mixture distribution and Bayesian statistics. That will be the part one of today's lecture. Part two will contain uh, some contents about random sum and some examples. So let us look at part one of this lecture. It's about mixture distribution and Bayesian statistics. Uh, Mixture distributions are useful for modeling populations consisting of several distinct groups. For example, suppose we are interested in a single variable, say height of people, but we can usually consider this height of people in a population as uh, a mixture of two distributions. One distribution is the distribution of heights of males. The other one is the distribution of heights of females. Right. So, suppose, for example, we know uh, the distributions of heights for these two individual groups separately. Then we are interested in finding out the distribution of the height of a person randomly selected from this population, where that person may be a male or a female. So in that case, we may be interested in finding out the actual distribution of the height of a randomly selected person from this population, right? So there we are interested in actually the mixture distribution, right? So like that, there can be several groups, not only two groups, there can be several groups where we are interested in a particular characteristic variable, but the distributions of that variable for different uh, groups will be different, right? So, but suppose, for example, in the population, these groups are mixed, and therefore, in a particular application, we are interested in what is the distribution of that random variable. If you take, if you consider a randomly selected unit from that population. So in that kind of situations, we are interested in mixture distributions. The overall distribution is obtained by combining the group specific distributions using the proportions of the groups as weights. Right. So in order to find out the mixture distribution, therefore we have to know, first of all, individual distributions for each individual distribution for each group. And in addition to that, we have to know the proportion of units belonging to that particular group out of the whole population. Suppose that Y is a binary random variable identifying the group, right? Here I'm considering only a situation with two groups. So where in that case Y will be 0 or 1, or you can call it 1 and 2 also if you want, just labels. Let f1x be the conditional distribution of the interested variable x given y is equal to 1, right? So that is the conditional distribution of the interested variable x for the group 1. And similarly, say f naught x uh, is the conditional distribution of the interested variable x for the group 0, denoted by 0, right? So you know already that this conditional distribution uh, is actually a function of x and y both for a given y. But in this case, we are giving a particular value for y. In that case, these conditional distributions will contain only x, right? If you are evaluating the conditional distribution of x given y at simple x and given value 1, so it's going to be a function of x. So therefore, it's just a function of x, and let's call it f1x. And similarly, the conditional distribution of x when y is equal to 0, because we are substituting the value 0 there, for y, in that case, it will be only a function of x. Let's denote that function by f naught x, just for the convenience. Otherwise, we can write down this whole thing. But to make it convenient, we will use this notation. Let the conditional distribution of x given y equal to y can be written in that case, right? If you have these two individual conditional distributions, then the conditional distribution of x for a given y where y can be 1 or 0, can be written in this particular form by combining these two, right? For example, if, for example, values that y can take are 0 and 1 in this case. So if y is equal to 0, this part will be 0, and this part will be 1 minus 0 times f naught x. So that is the same as this one, right? So that is fx given y equal to 0. Right? And similarly, fx given y at some x with y equal to 1 will be equal to 1 times f1x times 0 times. So this part will be disappearing. So you'll get 1 times f1x, which is the same as this. Right? So therefore, we can write down in general for a given y, we can write down the conditional distribution of x given y as this. In this case, y can take only values 0 and 1. If simple y is some other value, then this will be completely 0. Right. So that is one way to write down the conditional distribution of x given y. Now we are going to look at uh, the joint distribution, not the joint distribution, the mixture distribution. So suppose that probability that y equal to 1 is some value p, right? So that is the proportion of units in the group 1 out of the whole population. And suppose probability y equal to 0 is therefore 1 minus p. We are considering only two groups at this point. So let us consider the events capital Y equal to 1 and capital Y equal to 0. They are mutually exclusive and exhaustive events in this case, because y can take only two values. They are the only values that it can take. And if y equal to 1, it doesn't become 0, and y equal to 0 doesn't become y equal to 1. Therefore, mutually exclusive. Hence, for any measurable set A in the sample space, the law of total probability gives you this expression. Probability that x belongs to A can be written as probability x belongs to A given y equal to 1 times the probability y equal to 1 plus the probability x in A given y equal to 0 times the probability y equal to 0. So therefore, we can write down that this one is equal to P. So P times this conditional probability plus 1 minus P. This probability is 1 minus P. Therefore, 1 minus P times this conditional probability. Now, let's take a particular event A, right? The previous expression is correct for any A. Now let us consider a particular A where A is a subset of the real line from minus infinity to some value simple x. Right. So in that case, the preceding result can be written as, in that case, the probability x belongs to A means probability x less than or equal to simple A. So therefore, that is equal to the cumulative distribution function of x evaluated at simple x. And therefore, that can be written as P times, in this case, so this will be probability x belongs to A given y equal to 1 means the probability x is less than or equal to simple x given y equal to 1. So that is the conditional cumulative distribution function. right? Conditional cumulative distribution function of x given y equal to 1. And similarly, the other term, 1 minus p times conditional cumulative distribution function of x given y equal to 0, right? So that is clear, I hope. Where fx is the marginal distribution function of x and fx given y is its conditional distribution function given y equal to simple y, right? So now we are interested in the uh, actual distribution of capital X. So in order to get the density function, we will differentiate the CDF with respect to X. So when you differentiate this one, this side, left-hand side, you get the density function of X. And from here, you get P. And then when you differentiate this one, you get the corresponding conditional density function. And when you differentiate this one, you get the corresponding conditional density function, this one. So according to our previous agreed notation, so this is going to be P times F1x plus 1 minus P times F naught x. So this is the density function of x when x, where x is the value of the characteristic of interest when the unit is randomly selected from the population, not from a specific group, but from any item. It can be any item from the population, right? So x is the characteristic that we are looking at. So that thus the marginal density function of x is a weighted combination of the two group specific densities where the weights are the respective group proportions. So you can see that this is the uh, group specific density function for the group 1. This is the group specific density function of x for group 0 or the other group. And these are the proportions. So the weights are the proportions. So this density function, fxx, is called the mixture density. Although the mixture densities are often unimodal, they need not to be, although mixture densities are often multimodal, they need not to be multimodal always, right? Usually, if the two specific density functions for the groups are quite separated, then the mixture will be having several modes. For example, in this case, if you have only two groups, it's possible to have two modes clearly for the mixture distribution. But of course, if the two specific distributions are not that much separated, but they are somewhat, they have a large part which are common, then usually the mixture distribution will have only one mode. So it will look like a single mode distribution, even though it is actually a mixture distribution of two specific distributions. Right. So in order to show this idea, I have prepared a graph here. I have two specific density functions here, one density function, and this is another density function. They are in dashed lines. They are not the same. The means are different. Standard deviations are different, and you can see they are actually quite separated. There's only a very little area with a with a positive probability and common values. Right. So for this one, if I calculate, for example, if for example now the population proportion of this density is 0.3, and if the population proportion of this density is 0.7, for example, then the mixture distribution of x will be like this black curve here. It's clearly it is having two modes. It's a bimodal distribution, right? So this density is given by 0.3 times f naught x. This is f naught x actually, and f1x is this one, 0.7 times f1x. If you have that kind of situation, this is what you are going to get. On the other hand, if the two specific group specific distributions are not well separated, they are they have a quite large set of x values, both common to both distributions, then the mixture may look like this, right? So you cannot identify two modes there. Uh, when you look at the mixture distribution, it looks like just a single mode distribution. Right. So therefore, just by looking at the histogram or the smooth density, we are not able to determine whether it is coming from two specific distributions or it's whether it's just a single distribution. Right. So in the examples, we were looking at two groups, but more generally, as I mentioned, if a population consists of k groups, say for example, with mixing proportions P1 up to Pk, where the sum of those P1 up to Pk is equal to 1 and each P1 up to Pk are greater than 0, greater than or equal to 0, then the mixture distribution, right, mixture density function will be in this form, right? So this is just a direct extension of what we had earlier, right? So it just sum of pi times individual densities, where pj's actually in this case, pj's are the weights, and these are the fjx is the density function of x for the jth group, right? Now, after observing some value for x, can we uh, guess or predict from which group that observation came? That is an interesting question, right? So that is, you may not be able to guess exactly correctly, but you may be able to say how probable that observation is from group one, and thereby how probable it's from group two, right? So therefore, an interesting quantity to look at is, for a given x value, what is the probability that observation came from group 1? That is the probability that y is equal to 1 given that x is equal to simple x. And similarly, what is the probability that y is equal to 0 given x is equal to simple x, right? Of course, this one, second probability will be 1 minus this probability. In this case, if you have only two groups, but this also can be extended generally for k groups. So this expression we can obtain using the Bayes formula, right? The Bayes formula was discussed. Bayes formula for random variables were discussed in the previous lecture, right? So please, if you have not looked at that, please go through that lecture video. So here I'm directly applying that formula here. This is actually, again, you can see that this is a direct similarity to the conditional the Bayes formula that we use when we are considering events, right? That is what you usually call the Bayes theorem, right? Bayes theorem, right? So when you know the conditional probability of some events in one direction, if you want to find out the conditional probability in the other direction, usually you use Bayes theorem. So this is very similar to that, and I have explained that in the previous lecture. So therefore, probability y equal to 1 given x is equal to simple x will be p times f1x divided by fx actually, right? So fx. So that is the same as p f1x plus 1 minus p f naught x. So this is fx. And similarly, probability y equal to 0 is given when x is equal to simple x given by 1 minus p times f naught x divided by fx, where fx is the distribution of x for the whole population. That is actually the mixture distribution, right? So now let us use those ideas, definitions, and theorems to answer a question. Right. So this is an example coming from Limitian course book. This is example 3.37 in that book. So this is again very similar to what I explained at the beginning, classification using height. So the question is, when you are a given height, can you guess whether a person is a man or a woman? That is the basic question. Suppose that the height distributions of men and women are represented by normal densities having means 70 and 64 and 74 inches and standard deviations 4 and 3 inches. So that means we know the specific distributions of the random variable height for the two groups, men and women. In addition to that, suppose we know the value proportions. In this example, we are assuming that in the population, there are men and women proportions are equal. Therefore, P is equal to zero point 0.5, right? But you can use whatever the information you have. For example, in Sri Lankan population, we know women population is little larger as a proportion than men's population. So in that case, P may be like, if you are considering P to be the probability that a person is man, so it will be like 0.48. The other one may be uh, 5.2, for example. Here, but in this example, I'm taking them to be equal values. A surveillance camera estimates the height of a suspect to be 68 inches. Right. 68 inches. Estimate the probability that the person is a man or a woman. Right. So we don't know, we cannot identify the person as a man or a woman, but the height is observed. So using that, we have to predict whether the person is a man or a woman. And similarly, using a posterior probability of zero point 0.5 as a classification criterion, show that a height threshold occurs where the two conditional densities intersect. Find the relevant threshold for this problem. So that's a completely new idea about the threshold uh, uh, value, right? Classification criterion and so on. So those concepts will be explained through this example. So here I have looked at a possible scenario, right? Because we are given that the individual distributions are normal with some given means and given standard deviation. So I have drawn those distributions here. Actually, what I have drawn here is, first of all, this one is P times the density of man. So not the density of man here, P times. So that is actually the whole contribution to the mixture distribution. P times the density of height for men is given by this one. Actually, I have both are actually well. Actually, this should be the men's one because we know that men's are because the legend here is somewhat wrong because here I have both in the same line type, but here I have given two line types. So by looking at these two distributions, we can assume that because we know that the men's height is 70, right, average. So this should be the distribution of men's times P here. We are taking P to be 0.5 in this case. So this is the distribution of the height of women times 1 minus P. Again, 1 minus P is also 0.5 here. Why this distribution is shorter? Because its standard deviation is larger, it's 4. The other one has standard deviation 3. So you know that the actually this is not the correct the density itself. This the proportion times the density. So this is actually not a actual density, and this is not an actual density. Actual density will be just the density of man and density of women. But this is the contribution I have shown because in the book also it has shown it like that. That's why I have drawn it here. But in my first picture, when I explained these things, these are the original distributions. Right? So this one is F naught and F1, right? So this blue one is F1, red one is F naught. Again here, the legend is somewhat wrong. Right. So the mixture distribution thereby I can calculate because I know the individual densities. So when I calculate the mixture density function, that's going to be, for example, zero point 0.5 times the density of men plus zero point 0.5 times the density of women. You can see that even though these have two different modes and some because there's a large amount of intersection here. So you can see the mixture density looks like having only one mode. Right. So these are the given information, the the distribution of x given y equal to 1. Suppose y equal to 1 represents the men's group, y equal to 0 represents the women's group. So x is the height. So the distribution of x given y equal to 1 is normal with mean 70 and variance 16, standard deviation 4. The distribution of x given y equal to 0 is normal with mean 64 and standard deviation 3. So the prior probabilities in this case, prior probabilities are called here the probability that y equal to 1, right? So that is what you mean by prior probabilities here. That means we know the probability of each group proportions. Y equal to 1 and y equal to 0 both have the same probability, zero point 0.5, right? So therefore, if pi x mu sigma denotes the density function of a normal distribution with mean mu and standard deviation sigma, the mixture density, therefore, we can write down in short notation as zero point 0.5 times the density function of a normal distribution with mean 70 and standard deviation 4 plus zero point 0.5 times a normal density with mean 64 and standard deviation 3. So that is the short form of the mixture density, right? So if you randomly select a person from this particular population and measure the height, its height will be like an observation coming from this mixture distribution. Right. So now we want to look at what is the probability that given that x is equal to 68, what is the probability that the person is a man? And similarly, thereby we can find out what is the probability that the person is a woman. If you want, right, that will be one minus the probability. So using the Bayes formula, we can get observed height. For an observed height of 68 inches, the posterior probability. So this predicted probability is called the posterior probability. This is in the Bayesian setup. Those are the names, right? Probability y equal to 1 given x equal to 68 is equal to 0 0.5 times f1x divided by fx. Right. So this whole thing, these things we can easily get using R. Right. This value can be obtained using R. This is actually the density, D norm at 68 with mean 70 and standard deviation 4. Right. And this is again obtained from a D norm function. These can be obtained from D norm. So when you simplify this, you get 0.62. So therefore, the estimated probability that the person belongs to the first group, that is a men's group, is approximately 6.62. So therefore, the probability that the person is a female is then 1 minus 0.62, that is 0.38. So anyway, the prediction is actually, because this is the larger probability, uh, we will predict that the person is a man. Right. Now, that is the answer to part one, right? Now about the classification threshold. So what do we mean by this classification threshold? Classification threshold is some value, say x star, at which the two posterior probabilities are equal. Right. So here we were looking at when x equal to 68. But for what value of x will we have the two posterior probabilities, that is probability y equal to 1 and probability y equal to 0, given x is equal to some x star, will be equal. So that is what you call the classification threshold. Right? So therefore, we want to solve this equation. Probability y equal to 1 given x is equal to x star is equal to probability y equal to 0 given x equal to x star. Right. So therefore, you can get a separate expression for this using the Bayes formula, and you can get an expression for this using the Bayes formula. So when you solve those two equations, finally you will get this expression. This is what you have to solve now to get x star. Right. Some parts will be cancelled out now because fx will be in both. Fx star will be in both values, so that will be cancelled out. Right. So therefore, only the numerators will have to be equal, right? So when you now in this particular case, we know that probability y equal to 1 is 0.5, probability y equal to 0 is also 0.5. Therefore, finally you get this expression to solve, right? So for what value of x star will this be equal? So that means we are looking at this particular equation. This is the density function of a normal distribution with mean 70 and standard deviation 4. This is the density function of a normal distribution with mean 64 and standard deviation 3. So we have to solve this equation to get x star. Right. So you can see that these both are exponential terms, right? So it's easy to solve this one. So x star is inside exponential. So it's easier to solve this equation if we take logarithm of both sides. Then we get this equation, and then we get a quadratic equation in x star, right? So when you solve that quadratic equation, you get two values for x star. X star can be 45.44 or x star can be 68.13. Right? So there are two possibilities. But of course, only one is practically possible because this number lies between the two population means, uh, whereas the other value is quite outside, right? So therefore, it is the practical relevant classification threshold, this number, not the other. Thus, the relevant solution is x star is equal to 67.7 inches. Thus, the Bayesian rule classifies a person as a woman when the height is less than 67.1 inches and as a man otherwise. Right. So that is what I mean by the classification threshold, right? And the probability of happening those will be zero point 0.5, right? So now I'm going to look at something not in the book, but this is practically important, right? So how do you decide the prior uh, proportions, right? Using prior probabilities, what you called earlier, right? The probability that y equal to 1 and y equal to 0. How do you know those ones? Practical, right? So there are several ways you can apply to find out that distribution. For example, using the population proportions, if you know, for example, from a previous census, right? That kind of things may be tabulated. Therefore, you can use those as the actual proportions. If the proportions of men and women in the population of interest are known, they may be used as prior probabilities. For example, if 48% of population are men, then this will be the prior probability distribution of uh, Y's. Right? Uh, Using the representative sample, this is what you practically do most of the times, but you have to have large enough sample to decide this. So take a sample, random sample from the population and then find out what proportion of men's and what proportion of women's are there, and then take them as the estimated values. So that is the second method. These estimates are appropriate only when the sample is representative of the population from which the person is selected. So for it to be a representative, it has to be a random sampling method, of course, most of the times if possible, and then a sample should be large enough. And then using external information, also sometimes possible. Right? Prior probabilities may also be obtained from census reports that I mentioned already. That is what you mean by known values, previous studies, administrative records, or other reliable sources concerning the population of interest. When the reliable population information is unavailable, or when the two groups are to be given equal importance, sometimes equal prior probabilities are assumed, like both probabilities to be zero point 0.5. Right? So maybe we don't know them, but they are equally important to us. So therefore, considering that equal importance, you may take the probabilities to be equal. Right. Thus, the equal prior probabilities used in the example are modeling assumption. So just an assumption. They mean that before observing the height, a randomly selected person is regarded as equally likely to be in either group. Right. It has to be a reasonable assumption, of course. Otherwise, uh, your answer is not going to be good. Right. So if you know that in the population, even though there is a slight difference, the probability can be considered as approximately equal, right, without much uh, deviations or variations in the answer. Right. If reliable information about the actual population proportions are available, those proportions would be generally uh, more preferable, right, than estimated values. Right. So that is one example. Let us look at another example. This again a practical situation used in banks, but of course in this case we are looking at a simplified version of that. Mortgage default. This is again coming from the Limiting course book. It's example 3.38 in the book. The decision on granting or declining a mortgage application is very important. The financial officer has records on 1,000 applications, previous ones. 900 applications did not default. So they have been given the mortgage. They are paying their mortgage on time and so on. They have not default. With family income following log normal distribution with mu1 equal to 5 and sigma 1 equal to 0.4 in $1,000. They have already observed that 100 applications have default. So 100 people have not been paying the mortgage. With family income log normally distributed with mu equal to 3.5 and sigma equal to 0.3. Right. So this when you say log normal distribution, you know there is a connection between normal distribution and log normal distribution. We have discussed this in an earlier lecture. Right. So these mu and sigma are actually the corresponding mean and standard deviation of the corresponding normal distribution. Right. If log x has a normal distribution, then x is said to have a log normal distribution. Right. So these means and standard deviations are therefore the means and standard deviation of log of the variable. Right. So in this case, we again have two groups. Let's say y equal to 1 denote non-defaulters and y equal to 0 denote defaulters. So according to the given information, then probabilities, prior probabilities are 0.9 and 0.1. Probability y equal to 1 is 0.9, that is 900 out of 1,000. And probability y equal to 0 is 100 divided by 1,000, that's 0.1. Let Z denotes the family income measured in thousands of dollars and define X to be log of Z. X to be log of Z. So when you say X has a log normal distribution, right? Z denote the family income measured in thousands of dollars. So X, we are told that X has a normal distribution. X has a normal distribution. That means log Z has a normal distribution. That means Z, the family income actually has log normal distributions. Right? Z has log normal distributions. Log of Z has normal distributions. So the conditional distributions on the logarithmic scale are X has a normal distribution when Y equal to 1 with mean 5 and standard deviation zero point 0.4 in thousands. And then for the group Y equal to 0, that is defaulters, the distribution of X is normal with mean 3.5 and zero point 0.3 standard deviation. So therefore, the mixture density, if you consider a randomly selected application, then the income X will be, the density function of income will be given by 0.9 times the normal density function at with mean 5 and standard deviation 4 and zero point 0.1 times the normal density with mean 3.5 and zero point 0.3. Okay. So we are interested in finding out the threshold income value, right? Below what value should we consider the application and give allow the or grant the mortgage, or actually above some value, below some value, that value will not be granted. So what is that value? That is the question. The income threshold is determined by equating the weighted densities, right? So zero point 0.9 times this normal density should be equal to 0.1 times this one. So actually what we are looking at is the uh, Bayes probabilities, but again, the term in the denominator is the same. Therefore, finally it becomes this expression. So that can be written as, by taking the logarithm, you can write down this, you can obtain this expression. It's becoming now a quadratic equation. So when you solve it, you get x star is equal to 3.985. Right? So x are normal distributions. They are not the actual income. Actual income is Z. So we have to decide whether the mortgage is granted or not based on the actual income, which is Z. So let's call it Z star is the threshold value. Z star will be then exponential 3.985, which will be $53.785,000. So therefore, according to this classification rule, an application is declined when the family income is below this value and granted when it is above this threshold. So that's how a simple Bayesian statistics is used in deciding whether a mortgage is granted or not for a given random selected applicant. Okay. So now I'm going to look at a different problem where this problem was discussed in the previous chapter also, but in that case I didn't discuss it at that point. I postponed to discuss it in this chapter because then we can discuss two approaches that the book has decided. The book has discussed one approach in chapter 2, the other approach in chapter 3. But here I'm considering that example in both approaches consecutively here, right? So let's look at the problem. The following example illustrates Bayesian statistics where, unlike the frequentist approach studied in this book, parameters are treated as random with distribution given a priority. Right. So in this case, actually, we are going to look at some parameters and we are going to assume distributions for those parameters as well. So what is this problem? Consider two teams such as two soccer teams. Suppose that you know that the first team has won both of its two games, right? So we have observations or data on only two games. They have won both games, whereas the second team has won three of its four games. So we have observations or data on four games, and we know that three of them, that team has won three of them. Which team should be regarded as better? That is the question. What is the better team? Equivalently, which team has a greater probability of winning a future game? That's actually, there are two questions. Which team is better is one question. Which team has higher probability of winning in a future game? So there is a different question. Right. Uh, so how do we answer this question? In order to answer this question, first of all, we have to define what we mean by better. Right? Which team should be regarded as better? So whenever to talk about, to decide which team should be regarded as better, we have to define what we mean by better. Right? So what do you think? It's possible that different people define this word better in different ways. So we will look at two approaches, or two or three actually in this case. Before proceeding with the solution, we make following assumptions. Actually, these are the assumptions, not the definition of better, right? We have to make some assumptions as well. So there are two teams and they have some data. They have won several number of games, but we have to assume here they have not competed against each other. These are the data from which they played against some other teams. So otherwise, it will be a direct comparison, right? The two teams did not play against each other, so that's an assumption. Thus, the results 2 over 2 and 3 over 4 were obtained in games played against other teams. So we'll assume that. And secondly, for each team separately, the probability of winning is a constant from game to game, regardless of the opposing team. So that's kind of a very strict assumption. We are going to assume that for, say, the team A, for example, the probability of any game that they are going to play has the same chance of winning. We know practically it is not like that. We know for if you are playing against a weak team, again, you have to define what you mean by weak. But generally, if it is considered as weak, there is a higher probability of winning for group A, not the team A, right? But here we are going to assume that the probability of winning is the same no matter against what team they are playing, right? We are going to assume that for both teams, right? For a team A, that probability may be some value, probability B some other value, but for the given team, it is a constant. That's what we assume. And then we will assume for each team, the outcome of any game is independent of the outcome of all other games they have played. So that's again a kind of very strong assumption because we know that actually uh, winning a game, may have a good moral when they go to the next team after winning a game. So they may have a higher chance because of that also. So they are not completely independent. But in this case, just for this example to answer this, we are going to assume that the outcome of one game is independent of outcome of another game. Right. So suppose that the probabilities that the teams 1 and 2 win a game are P1 and P2 respectively. So for the team 1, we are going to assume probability of winning any game they are playing is P1. For the team 2, it's P2. They are constants. Usually in our classical or frequentist approach, we consider them as constants. Under the above assumptions, the probabilities of the observed results are going to be P1 to the power 2 because they have won both games. For the other group, they have won 3 out of 4 games. So using the bivariate number of games they win is has a binomial distribution in that case with n equal to 4 and probability of success equal to P2. So the probability they have won 3 games. So the probability of what we have observed is given by 4C3 P2 to the power 3 1 minus P2 is given by that. So these two expressions are actually so called the likelihood of winning. Likelihood of winning is they are not because we have already observed this thing. So what we are looking at is the probability of happening such a thing, but we are considering it as a function of P, P1 and P2. Right? So when you look at the probability of happening something similar to what we have already observed, considering it as a function of a parameter is called the likelihood function of that parameter for the given event or for the given data. Given the observations, we are looking at what is the probability of happening similar thing if P was some value, say P1. Right? So that's called the likelihood function. So that's why we denote them by L here. So this expression we denote by L1 P1 because it's a function of P1 and this is L2 P2. Of course, they are two different functions. Therefore, L usually denotes the likelihood, but of course, they are not the same likelihood. So that's why I use L1 and L2 to denote the two functions. So when regarded as functions of the unknown probabilities P1 and P2, these expressions are called the likelihood functions for the observed results. Likelihood functions. So what we are interested in is one way to find out or define the better team is find out the larger value of P1 or P2. We find out which of those two are larger than the other. And then the team with the larger P can be called the better team. That is one possible approach. Of course, we don't know those P1 and P2, right? So in that case, what we can do is we can estimate P1 and P2 using some method. One method that is used in general is called the likelihood method or maximum likelihood method. Maximum likelihood method. So you look at what is the value of P1 that gives you the maximum likelihood of happening an event like what we have already observed. Right. So we look at this function as a function of P1 and find out what is the value of P1 that gives you the maximum likelihood of happening what has already been observed. And similarly, you can find out what is the value of P2 considering this as a function, where does this function has its maximum. Right. So you can easily do that by mathematically taking the derivative with respect to, in this case, P1 and equating to 0 and solving and then showing that at that point there is a maximum and similarly for this one. That is one method. Or you can look at a simple graph. That is also possible, and find out approximately those points where the maximums are occurring. That's also possible. But regardless of whether you use the derivative method or the graphical method, estimates in this case, this example, will not be very reliable because these likelihoods are based on only a few observations. In the first one, only based on two observations. In the second one, only four observations. So therefore, it is obvious, right? Whatever the estimates you obtain based on a small number of observations are not that reliable. But anyway, we will look at those values and then find out according to that method, right? Even though the estimates are not that reliable, we will just follow the method and then see according to that definition that we discussed, right? The team with a higher probability of winning will be taken as the better team, right? So here are the two likelihood functions. This is the likelihood function for the team that won two out of two games. This one uh, is the likelihood function who won two out of three. Was it two out of three or three out of four? I don't know. Actually, the problem gives you three out of four games, but here I have drawn something wrong here. But method will be the same. Oh, maybe my legend here is wrong, but this is the correct function. I think that is the case. This is the correct function, but the legend is wrong here. But assuming that these are the correct graphs, we can easily draw these graphs now. Right? So this graph and this graph we can look at. So where does the maximum occur? Maximum of the likelihood occur here when P is equal to 1. So therefore, my estimate for P1 will be equal to 1 in that case. Of course, because they have won two games out of both two games. The other one, here, this is where the maximum occurs somewhere here. So that is actually 2 out of 3. So this is not the correct uh, function because here I'm considering winning two games out of three games. Right? So if you apply this thing for 3 out of 4, actually, the maximum will occur uh, around 0.75, right? 3 or 4, somewhere here. So this is not the correct one. But let us assume for this one, uh, because the method will be the same, right? Suppose these are the correct graphs. So in that case, those will be the estimated probabilities. And thereby, we might declare that as the first team as the better team. Right? So one way to answer the question is to estimate P1 and P2 by maximizing their respective likelihood functions. That is what I explained. And then declare the team with the large estimated probability of winning to be the better team. However, because these likelihoods are based on only 2 and 4 games, respectively, the resulting estimates may not be reliable. So we have to know, even though we have estimates, they are not that reliable. Let's look at another approach that we can use. This is the approach that actually book has discussed in chapter 2. Another possible approach is to assume that the two observed results are equally likely and hence set LP, L1P1 is equal to L2P2. Right. So that means assume for the moment that the likelihoods of happening what has already happened are equal. We may then compare P1 and P2 subject to this condition and declare the team with the larger winning probability to be the better team. So there will be some P1 and P2 values to satisfy in these two, no? So find out, considering this as a criterion, find out under what values of P1 and P2 this will satisfy. And thereby find out P1 and P2. And then the value with larger P will be considered as the better T. So that is the approach that the book is taking, right? However, this approach is only heuristic. It's not very justifiable, right? Assuming that both events that has already occurred have the same likelihood is not a very justifiable assumption. But nevertheless, that is what the book is applying. Uh, Observing both results does not by itself provide a statistical justification for equating their likelihoods. Right? So it seems that the book is saying that both has happened already for these two groups. So why not consider they have equal likelihood? That is the kind of argument underlying this mathematical expression here, right? So anyway, even though it's not very justifiable because it's the method that the book has explained, let us look at that method. So let's consider some values of P. This is the same graph that we had here earlier. These are the two likelihoods. Of course, that earlier error is still there, but the mathematical argument will not be affected by that one because 2 out of 3 or 3 out of 4 is not going to change the mathematical argument. So, for example, let's consider several P values, values of P1 and P2, and see what happens, right? Right, because we are looking at the values of P1 and P2 for which the likelihoods are equal. Right. So let us take, for example, consider where P2 is equal to 0.4. So I will look at the likelihood L2. L2 is given by this dashed line. So L2 at when P is equal to 0.4 is this value. So what is the value of P1 where the L1 had the same value? That value is somewhere here. If you draw a horizontal line, right? This is the value of L2 now. But this one will have the same value. L1 will have the same likelihood when P is equal to something like 0.537 according to this. 0.537. This value is 0.537. Right. So in that case, so P1, if P2 is equal to 0.4, P1 has to be 0.537 for the likelihood to be equal. So if that is the case, then P1 is greater than P2. So this heuristic method declares in that case team 1 to be better. But on the other hand, if we take, for example, P2 to be, say, like 0.8, in that case, this is the height of the likelihood L2. The value of P1, where L1, P1 had the same likelihood, is somewhere close to 0.6. P1 is equal to 0.62, somewhere here, right? This line crosses this L1 function here. So if we come back to the horizontal line, it's going to be 0.62. So in this case, P2 is 0.8, P1 is 0.62. So then our decision will be different. In this case, P1 is less than P2. Therefore, the heuristic method will declare that team 2 is better. So it is not true that for any P2, always P2, where the likelihoods are equal, P1, if you compare P2 is always less than P1 or P1 is always less than P2, right? So the values of P1 and P2 where the likelihoods are equal depends on what value you consider as P2 and then the P1 will be different, and therefore the inequality between those two can also be different, as we saw. Therefore, using this method, it is not easy. It is not possible to declare one team as the better team. So therefore, according to this criterion, using the data we have, the decision, we don't have a decision actually. Decision is inconclusive, right? So to look at it more mathematically, what we looked at was graphical. So if you are looking at the same problem mathematically, you will be equating the likelihoods and then finding out uh, P1 and P2, and then finding out whether P1 is greater than P2 or P2 is greater than P1, and thereby we can define. But mathematically, we'll see that the expression L1 P1 is equal to L2 P2 will be this one. So from this one, we can get this expression, for example, P1 divided by P2 is equal to this one. Right. So now, if, for example, P1 that we consider is greater than P2, or like P2 is less than P1, as we looked at in the graphical situation, right? Well, like what we look at is P1. If P2 is less than 2 over 3, 2 over 3 is actually this value here, right? So if P2 that we considered, right? In this situation, P2 that we considered is 0.4 and it was less than 0.6, 203. So in that whole area, whatever the value that you are considering below this point here, in that case, we will see that P1 is greater than P2, right? So for example, if you consider some other value here, right? And then P1 value will be this, P1 value will be in this case, this one, right? P1 is greater than P2. P2 is point somewhere, like if you consider this one, then of course P1 is going to be right to that. So therefore P1 is greater than P2 in that case. If P2 is 203. If P2 is equal to 203, right, at this point, both are crossing each other. So in that case, P1 will be equal to P2. Still, we will not be able to declare one team as a better team. In that case, we will declare them as equal teams. On the other hand, the P2 that we are considering is above 203. Then, like what you look at in the graph, right? So if you consider this value or any other value here, right? Sometimes you will not have, yeah, if you consider some value here, then the P1 value will be smaller than P2. And thereby you will declare that the group 2 is better, right? But of course, in general, we cannot declare one group as the better team, one team as the better team, because we don't know what the value of P2 is, right? If we knew what the value of P2, of course, we could have decided which team is better team according to this one, according to the criteria that L1 and L2 are equal, right? But in this case, the conclusion is not very clear. Again, it's a inconclusive decision in this case. So now we are going to look at another approach that is discussed by the book in the chapter 3, kind of a Bayesian approach. This is where we are going to assume something about that unknown probability P1 and P2. Right? Instead of just considering them as some two constants, P1 unknown constants, what we are going to assume that is that they have some distribution. Suppose P1 also has a distribution that is called the prior distribution, right? Of course, in this case, we are applying something called uninformative prior. We don't have any idea. But this is, on the other hand, is also a conjugate prior, something called in Bayesian settings. Uniform distribution is a particular case of a beta distribution. And in the previous example, we talked about the conjugate distribution, right? We show that beta distribution is the conjugate distribution of the binomial likelihood, right? When you have a binomial likelihood, the conjugate distribution that you use as the prior is the beta distribution usually, right? So in that sense, that is why we are using P1 and P2 to be beta. That's why that we are going to assume that P1, P2 both have uniform 0, 1 distributions. In other words, they are the same as beta 1, 1 distributions. So another alternative method is to treat P as a random variable having a uniform distribution and regard the binomial probabilities as conditional probabilities given P. Binomial probabilities are the probability that the number of wins is equal to 2 and number of wins is equal to 3 and so on. So let P1 and P2 denote the winning probabilities of teams T1 and T2. So now they are random. Therefore, that's why I have denoted them by capital P1 and P2. Right? Earlier, we denoted them by simple P1 and simple P2. They were considered as constants. Right? I would have used Greek letters instead of P1 and P2 because they are unknown constants also. But again, the book is using P, therefore I used P. But here I have been careful to distinguish them as, in the previous situation, a constant and now a random variable. So let P1 and P2 denote the winning probabilities of teams 1 and 2 respectively. Assume that they are independent and have uniform prior distribution. So equivalently, assume that they are beta 1, 1 distributions. So therefore, according to the given information, now we can frame the problem as x1, x2 with the number of games won by teams 1 and 2. Then the conditional distributions are binomial with the number of trials equal to 2 and some P1 here, where this P1 is the given value, right? So here we are looking at the distribution of x1 given P1 is equal to some P1. So in that case, when the given value is P1, of course, the distribution has that P1 here. Right? For x2 also, we are assuming that binomial distribution with n equal to 4 with a given P2 here. Right? So notice that now capital P1 and P2 will have distributions. So because P1 and P2 have uniform prior distributions on 0, 1, the prior density functions will be just 1 here. Not only because uniform, even if you consider them as beta, the density function will be given by this one. So here the prior density is denoted by pi, right? It's a difference. There's a difference between the usual density functions are denoted by f usually, but the priors are denoted by pi's here in the book. Right. So therefore, I denote them by pi1 p1 is equal to 1 when p1 is between 0 and 1. So this is actually uniform distribution, and pi2 will be also given by this. So these are called prior distributions. For each team, then the Bayes theorem gives you the posterior. So the previous Bayes result now gives you the conditional probability is called the posterior density. These are the names used in the Bayesian setting. So pi here denotes the posterior conditional distribution. This is a conditional distribution. The conditional distribution of P given X. Right. So in order to be correct here, the usual notation, there has to be some subscript capital P given capital X, for example. But to make it simple, we have ignored that part. So this means the conditional distribution of capital P evaluated at simple P when capital X is equal to simple X. So that's what this means. So from the Bayes formula, that will be this expression, right? The conditional distribution of X given P times the distribution, marginal distribution of P. In this case, it's the prior distribution. And then in order to get the distribution of uh, x, you have to integrate this thing with respect to uh, p, or in this case, because we are assuming p equal to u here, because we are so the integration with respect to u, but become from 0 to 1. Right? So we are integrating with respect to p, but in this case, uh, to make it clear, we are using a different label for the variable of integration. Right? Otherwise, this would have been p equal to simple p pi of p dp. That's perfectly correct. Right. So if I apply the known things now, right, if I apply the correct expressions here, these are the expressions that I get, right? This is the uh, this is the binomial distribution of x1. This is the conditional distribution of x1 given p is equal to p1. It's a binomial probability. And then if you multiply that by, so this is actually a likelihood function. If you consider it as a function of P1, right? Otherwise, it's a probability, conditional probability. If you consider P1 as a fixed value, multiply the likelihood. So this can be called as a likelihood function of P1. By the uniform prior, you get the uh, you get a constant times the posterior, but you have to find out the constant to make it a proper density, right? So you have to have a normalizing constant. The normalizing constant is given by the integration of this one from 0 to 1, right? You cannot take this one directly as the posterior density function because the integration of this one will not be giving 1. So you have to normalize that this expression by the normalizing constant to make it a proper density, right? Posterior density of P1 will also be a proper density. So in this case, the normalizing constant will be 1 over 3. Therefore, the posterior density of P1 will be given by the expression divided by the normalizing constant. So that's this one. So that is the posterior density function of P1 given x1 is equal to 2, given the observed value of x. Right. Now, if you compare this with the usual beta distribution, we can identify this as actually a beta distribution, right? So the usual beta distribution has this form, some constant times p to the power alpha minus 1, 1 minus p to the beta minus 1. So if you consider this expression, compare with this one, you will see actually this is the same as the density function of a beta 3-1 distribution, beta 3-1 distribution, right? Because you can see that here alpha is equal to 3. That's why you get 2 here, alpha minus 1. Beta is equal to 2. So therefore, this part will be 0 and therefore 1 minus p will not come into the density. And this quantity with alpha equal to 3 and beta equal to 2 will be equal to 3, right? According to the definition of beta quantity. Right? So therefore, it's a beta distribution. So when the that's why we say uh, the 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 conjugate density, right? The choice of conjugate density gives you the answer, final answer also in the same kind of family, right? Posterior distribution for team 2 will be given by this expression, right? First of all, this is you can interpret it in two ways. This is the conditional distribution of x2 given p2 is equal to simple p2. That is one way to look at it. Or you can consider this as the likelihood function of p2 given x2 is equal to 3. That is the likelihood function. That is called the likelihood function in that case, right? So in order to get the posterior distribution, you have to multiply it by the prior distribution. So prior distribution is just 1. Therefore, you get the same expression. Now, when you compare this with the usual beta distribution, you will see that again, this is a beta distribution. After normalizing, of course, right? You have to calculate the normalizing constant. Otherwise, it's not a density function, but the form of that is a form of the beta distribution, right? So even though you don't know the exact uh, beta distribution, once you identify the form of the density function, you will be able to guess the normalizing constant because it has to be a proper density, right? So we can identify it as a beta 4 2 distribution. Therefore, of course, the normalizing constant has to be 1 over beta 4 2 beta 2 beta 4 2 constants, right? But here we have found out the normalizing constant in the direct way by integrating the expression that we got, right? So even if you calculate it use as a 1 over beta term, you will get the same answer. So therefore, now in general, we can see the both results, right? Posterior distribution, right? In general, we can see that posterior distribution for given x is going to be a beta alpha plus x and beta uh, plus n minus x. So this is the first parameter, shape parameter. This is shape parameter 2, right? So depending on your alpha and beta, this will be different, but both answers, both posterior distributions and have this form. So in the present example, the uniform prior is beta 1 1. Consequently, we got posterior distribution of P1 given x1 is equal to 1 is equal to beta as a beta 1 plus 2 and 1 plus 2 minus 2. So there in that case, you can see that alpha is equal to 1, x is equal to 2, right? And then beta is equal to 1 also. And therefore 1 plus 2 minus 2. Right? So beta n is equal to 1. Well, n is equal to 2, right? We have two observations in binomial case, but beta is equal to 1 and 2 minus 2. So therefore this beta. And similarly, P2, posterior distribution of P2 given x2 is equal to 3 is this distribution, right? So therefore the posterior density functions are these expressions, we already have got them. They both are proper densities. So now, how do we decide which team is better? Right? We have now posterior distributions of the probability of winning. The probability of winning is not now a constant. We are assuming it's a random variable. So we now know the posterior density functions for both groups. So how do we find out a quantity, a single quantity to look at and then compare those two to decide which team is better? What we look at is, for example, one thing we can look at is what is the probability that P1 is greater than P2? If that probability is greater than 0.5, we'd say P1 is greater than P2 with more than probability 0.5 and therefore team 1 is better. That is one way to do it. So therefore, we have looked at that method. We have calculated the probability that P1 greater than P2. Of course, here we have to get the joint density of P1 and P2, joint posterior density. But we can obtain it easily because P1 and P2 are independent. Therefore, the joint posterior density will be equal to the product of individual posterior densities, right? So in order to get this probability, what we have to do is we have to integrate the joint posterior density of P1 and P2 with respect to P1 and P2 like this, right? So in this case, P2, if we are integrating from P2, P2 will be going from 0 to T1, P1 will be going from 0 to 1. Right, because we are looking at probability P1 greater than P2 subset, right? The support for P1, P2 jointly is just a square. On one direction is from 0 to 1, from the other direction is from 0 to 1. So that will be a square, but we are looking at the volume under the joint density over a subset satisfying P1 greater than P2. So when P1 is greater than P2, when you are integrating with P2, P1, P2 will be changing from 0 to P1, right? So this kind of examples we have looked at several already. Therefore, please look at the previous video if you want to understand. I recommend you to draw the uh, support of the joint density and then mark this event as a subset of the support, and then you will be easy to, it will be easy for you to understand why this integration limits are given by this. So finally, we have found out the probability P1 greater than P2 to be 0.64, right? So which is greater than zero point 0.5, and therefore, according to this method, one would decide that uh, team 1 is better than team 2, right? There is a probability on average, right? We are not on average. The probability that P1 is greater than P2 is larger here, greater than zero point 0.5. And consequently, the other one will be smaller here, right? Probability P2 less than P1. So, of course, so thus, based on the uniform prior distributions and the observed results, there is approximately 64.3 posterior probability that team 1 has the larger winning probability. Under the rule of selecting the team whose winning probability is more likely to be larger, then we would claim that team 1 would be the better team, right? Team 1 would be declared as the better team. So that is one approach. So there was another part in the question. What is the which team has the higher probability of winning a future game? Right. So for a single future game, the posterior predictive probability that the team I wins is obtained by averaging its unknown winning probability Pi over its posterior distribution. Right. So that's what we usually do to predict the future values. We consider the average over all possible p-values over the prior distribution. Therefore, the posterior predictive probability is equal to the posterior mean of pi given xi is equal to simple xi. So, for each posterior distribution and for each team, posterior distribution of P1 and P2, we have those expressions. We know both them are beta distributions. So what are their expected values, right? Now we know theoretically for a given beta distribution how to get the expected value directly using the known formulas. So in general, if some random variable say P has a beta alpha beta distribution, then expected value of that is equal to alpha over alpha plus beta. Right? So we knew that we have already found out that P1 given, so this is the posterior. P1 given x1 is equal to as a beta distribution with 3 and 1. Alpha is equal to 3 and beta is equal to 1. So therefore, according to this one, we can find out the expected value of P1 will be equal to 3 over 4. Similarly, P2 also has a beta distribution, posterior distribution, and therefore the expected value is equal to 2 over 3. So therefore, according to these two values, also the probability of winning a future game is larger for team 1. Therefore, the posterior predictive probabilities of winning the next game is 4 over 3 for team 1 and 2 over 3 for team 2. So thus, according to the posterior predictive probabilities, team 1 has the greater probability of winning its next game.